In this video module, we're going to take a look at the time value of money and consider some of the different metrics and concepts that we deal with when we're considering time value of money or present value equations. First, we're going to take a look at the changes in value over time. Then we'll look at the 5 basic variables that we think of in the time value of money equation. Then we'll look at the present value or time value of money equation itself. Then we'll rearrange that and use future value, FV, equals present value times 1 plus r to the t. And then we'll rearrange it again as we think about a time value calculation of present value, or PV, equals the sum of beta t divided by 1 plus r to the t, which is a multi-term equation that we can think of for time value of money as well. And then we'll also take a look quickly at how we think about using our HP 10B2 calculator to solve time value of money problems. Let's think about changes in value over time for a minute. I know that $1 today is worth more than $1 tomorrow. Think about this. If I buy 5 apples today and it might cost me $5, versus in 5 years, I might be able to, with the same $5, only buy 3 apples. Well, it's not the value of the apple that's changed. An apple is an apple is an apple. But the money that I'm using to buy the apple has changed, and we call that change inflation. So inflation is simply an example of one of a number of different discount rates that we might consider that have an effect on the value of money, the value of currency. But we can use those discount rates to think about the present value in today's dollars of a monetary exchange in the future. We think of this as being a discounted present value model, or maybe sometimes thought of as discounted cash flow models. The discount rates might be an inflation rate, or when we're thinking about a monetary asset rather than a physical asset like an apple, maybe the discount rate we're thinking of is the cost of capital. Or maybe it's just an opportunity cost that we have to think about. An opportunity cost would be the best alternative, or the next best alternative. And then finally, an investor might think of this discount rate as a required rate of return. So a discount rate, which is going to be active in the denominator of our basic time value of money equation, a discount rate is going to be different depending upon what we're trying to accomplish. So let's go a little further here. There are 5 variables that we commonly consider when we're looking at time value of money equations. They are PV, or present value, FV, or future value, beta, and beta is just some cash flow or some monetary exchange. R, which is our discount rate, and T, which is time. So these are the 5 basic variables that we'll consider in this construction. So now let's briefly think about what the basic time value of money equation is, the present value equation. The present value equation, not surprisingly, uses the variables that I just noted for you. But it doesn't appear as though I have future value here. And in fact, I kind of do, and I'll help you understand where it exists in a moment. So the basic time value of money equation, if we're thinking about one monetary exchange, an amount of money today compared to amount of money in the future at a single point in time, is present value is equal to beta t, or just some cash flow, divided by 1 plus r to the t. Well, let's look at this for a moment. In this case, I use t as an exponent in the denominator, or t for the number of periods of time that I'm dealing with. And we'll think about this at the moment as though these periods are measured in years. I also use t as a subscript to my beta, or cash flow variable. And in the case of the numerator, where I use it as the subscript, it's simply a descriptor. It just tells us something about that cash flow. It doesn't do anything. But as I use the t, which will be the same t, of course, when I use it in the denominator, it actually is an exponent. So it's a financial operator when I use the denominator. Well, in this case, I've got PV, or present value, being equal to beta, or some cash flow at time t, divided by 1 plus r, or my discount rate, to the exponent of time t. Well, where do I have future value? Well, if you think about this, when we have a one-shot scenario, so we're exchanging currency one time, we're looking at the present versus some future cash flow. Well, in this case, beta t is the same thing as future value. So we're actually looking at the exact same thing here. So now let's go yet further still, and we'll look at using future value is equal to present value times 1 plus r to the t. So we're going to rearrange some equation here. We started, of course, with present value being equal to beta t divided by 1 plus r to the t. If we can agree that beta t, since this is a one-shot transaction, might be future value divided by 1 plus r to the t. And if we want to then think about how would we solve this equation normalized on future value, or using future value as the item we're solving for, then we can rearrange it. We have present value is equal to future value divided by 1 plus r to the t, or we can say present value times 1 plus r to the t is equal to future value. And all I've done here is I've multiplied each side of the equation by 1 plus r to the t. When I multiplied it over on the right-hand side, it then essentially got rid of it from the right side, and I multiplied the left-hand side. So this is a future value equation, whereas this is a present value equation. It stems from the exact same algebra. It's just we're using it slightly differently.